Good morning, everybody. I'll try and speak quite loudly so that I could move around a bit, not stuck behind here. Today, before I start, I'd like to give you just an overview of dormancy, things that we know, but luckily, or hopefully I'll be laying a base for some of the talks to come. We all know that deciduous fruit need to go dormant during winter. They need a certain amount of chill so that they can go into dormancy and come out again in springtime. This is the endodormancy we're all familiar with. And there are also other types of dormancies. If you read Lang et al. And the terminology of that, we know that there's paradormancy and ecodormancy, and this is roughly the status quo of the dormancy progression in a tree that receives sufficient winter chill. We also know that this picture changes completely when we have warm winter conditions. We have prolonged endodormancy, we have much more paradormancy and very little ecodormancy in warm winter conditions, and this results in delayed foliation and some of the symptoms that Vian was referring to earlier. And we also know that this is the reason why we need rest-breaking agent, because this dormancy progression changes and doesn't happen the way it should happen in a warm area. We also know that our success with rest-breaking agents are often different from year upon year. For example, in an area, year upon year receiving exactly the same amount of chill, let's say 650 chill units, the same exact rest-breaking application, but we do see the success in bud break being different. And that leads us to believe that the absolute amount of chill that we receive during the winter is perhaps not as important as the way that this chill is distributed throughout the winter season. And with what we're doing here is we actually have a good reason to believe that the secret lies within this induction period, the autumn temperatures, daily autumn temperatures, and the effect thereof on the whole progression. And with this study, we are investigating this induction period by giving additional chill and then looking at the differences that we see. So what did we do? We collected royal butte shoots from two areas, climatically contrasting. Koa-Bokkerveld is a cold area, Elgin as your warmer area, and we sampled these every week throughout the winter period. So we would go out, cut shoots, bring them to the lab. Before we force them and look at their dormancy level, we would actually give them additional cold. And here you can see the treatments. We gave them different temperatures and different durations, and over here in brackets you can see the amount in chill units of additional cold that we gave these shoots to see how that affects their behavior. Then we would take them into the forcing conditions and we would monitor bud break to look at that. Let's look at some of the results from the Koa-Bokkerveld. Here you can see a graph where we can clearly see temperatures, the dotted line declining over the winter period. And then these solid lines are the dormancy progression curves, the thick black line being the control that received no extra chill. And the mumbo-jumbo colored lines are all the different treatments. To take home from this would be that in a cold area, you can see that during this induction period, the different additional cold treatments behaved quite similarly to the actual control, the black line. There were some changes, but in general the behavior was the same, meaning that in a cold area, there's little sensitivity to cold in autumn. The buds seem to show little sensitivity towards the cold. We did see differences here. Maximum levels were slightly higher with additional cold, and definitely coming out of dormancy. The mumbo-jumbo lines, treatment lines, are all below the control, so you can see that the additional cold actually pulls those shoots out of dormancy sooner and faster. And the cold area, let's compare that to a warm area. Here it looks different. Again, we see the declining average daily temperatures and the dormancy progression. First of all, we realize that something is happening here in that induction period in a warm area. The treatments do seem to have some effect here. The treatments behave differently from the control, meaning that the additional cold that we give does affect shoots in a warm area, meaning that they are more sensitive to chill compared to the cold area in this period. So much so that you can see the treatment lines all being above the black control line here, pulling them into dormancy sooner. And also, but the interesting effect is that it doesn't seem to have any effect when it's coming out of dormancy. Well, actually, it's not coming out of dormancy at all here. The additional chill is not helping the trees to actually come down from dormancy. This is the kind of contrasts that we see that give us insight into the dormancy behavior in these two different areas. To put that into conclusion, we can see that for the induction of dormancy, the warm area is more sensitive to additional cold. Entry happens sooner. Maximum levels are equal, not necessarily higher like we saw in a cold area. And then the exit from dormancy in the warm area had no effect. The additional cold had no effect. As I said, this gives us insight into what happens with shoots or buds in a warm area and how they differ. This assists us greatly in understanding the behavior and trying to come up with better ways of researching this problem that we have, and helping us to develop more practical horticultural practices that can address the challenges that come with warm winter areas. Thank you.